Okay, so today I'm going to show you where that, so if you think about, you learn in AP Physics 2 or Physics C, depending on how your teacher taught it, you learn that the magnetic field due to a wire of holding a current I, a distance r away, is equal, so the magnetic field at that point is equal to mu naught times I over 2 pi r. And if you're in physics too, that equation is just handed to you, right? Like you just, and intuitively it kind of makes sense, right? So it's like if you have more current, you get a stronger magnetic field. If you're farther away from that wire, it's going to be a weaker magnetic field. Just like if you're farther away from a planet, there's less gravitational force. So that it kind of makes sense, but you know, where does the 2 pi come from, right? Like where does this equation like exactly come from? That's what I'm going to show you. I made a video on Biot-Savart law, so you should check that out because I'm going to use that to show you where this equation comes from. To derive this equation, what you got to look at is, let's say there is a wire. Okay, first I should use red because this marker's like low-key dying, and you know I gotta get new ones. And red isn't. I know red isn't that dark, so just try to watch. Let's draw a little coordinate grid here. So if this is the y-axis, and this is our x-axis. Let's say there is a piece of like a section of wire, right? I'm gonna draw in. I'll draw it with a little bit of thickness, kind of like a rod. And if you remember from electrostatics, you might see where this is coming from. Let's like physics-y electrostatics. Let's say we want to find the distance or the magnetic field at distance. I don't know. Let's just say r. How about that? Or do you want to use r? I was gonna say r because that's in the. Let's use x. Why not? At a distance x initial, whatever. From at point P, right? So you want to find the net magnetic field at that point, P, x initial away, and the length of this section of wire is going from A, or I should say like the top of the wire is at a y coordinate A, and the bottom of the wire is at a y coordinate negative A. Total length is 2A. So I gotta find what is the net magnetic field at point B. Let's say the current is going this way. So what you can use is you can use right-hand rule, and you're gonna realize that or actually let's do this first. How do we find the net magnetic field at point P? Well, we know that from Biot-Savart law. Biot-Savart law tells us that current can create magnetic field. So there's gonna be a very small section of current here, or wire here of length dl. Like a very small section of wire, and that is going to be, let's say this is, or let's draw this up here, why not? So dl, and that's going to be kind of a height, we'll say y above point P, and that distance from the small amount of current or small amount of wire dl, that distance is, if you use Pythagorean theorem, it's going to be square root x initial squared plus y squared, right? So there's also, and Biot-Savart law tells us that the magnetic field, I'll say dB, right? So the small amount of magnetic field dB created by a small amount of section of wire dl is equal to mu naught 4 pi times I dl cross r hat over r squared. So why am I saying dB? Well, this small, this amount of wire is creating a certain magnetic field, but so is this section of wire, and so is this dl, and this whole thing is made of dl's that are all contributing to the magnetic field at point P. And what's nice is they're all in the same direction, so I don't even have to work. So if you remember from electrostatics, when you're finding the electric field due to a rod, you have to worry about like the direction and cosines and sines and all that kind of stuff. We don't got to worry about that because if you use your right-hand rule, my thumb is pointing up, the current is going to swirl around it like so. All the magnetic field created by each thing is going to go into the page. So we're going to have to do a sign here in a second, but we don't have to worry about direction. All the directions in the same, like, it's all in the same direction. The magnetic fields individually, dBs, all the dBs are in the same direction. So what I can do is now I should integrate this, right? Integrate each of the little thingamabobs. I should integrate all the DLs. So let me take the integral, right? So I get the net magnetic field is equal to mu naught, I can pull it out, right? I can even pull out the I, right? So mu naught I over 4 pi times the integral. Instead of L, let's just call this dy. And you're going to see why in a second. Dy cross r hat over, what's r squared? Well, r, the distance at a certain dy or dl, it's just square root x squared plus y squared, all of that squared, right? So the square will cancel out. You're going to see here in a second. Square root x initial squared plus y squared, that's going to cancel out. Let's deal with this cross product here, cross r hat. If you remember from the Biot-Savart law video, when you're doing the cross r hat and you're only worried about the magnitude, right? Because we don't have to worry about direction. When you're only worried about the magnitude, this cross r hat is really just dy times sine theta, and it's because when you're taking the cross product of a unit vector has magnitude 1, so it's really just dy times 1 times sine theta. When you're taking the cross product, the r goes away, the r hat goes away because it's times 1. So dy sine theta, it's a theta in between the distance or the position vector and the dl, the current. So it's this theta, right up there. What are our bounds? Well, when we're integrating on the y-axis, we're going from negative a to a. Hopefully that makes sense. B is equal to mu naught I over 4 pi. What's sine theta? Well, sine theta, it's opposite over hypotenuse. X initial over square root x initial squared plus y squared. So dy, I'll do it like this. So this becomes x initial squared plus y squared times x initial over square root x initial squared plus y squared. And oh boy, you can probably see where this is going. So mu naught I over 4 pi times the definite integral negative a to a dy times x initial over x initial squared plus y squared to the 3/2 power. Hey, that's an integral that you see a lot in Physics C, E, and M. And I made a video on it, so you can watch how to evaluate this. To evaluate, it's usually given. I'm going to really quickly just pull out the x initial though. We can put it with our constants we got over here, because remember that distance is a constant. So when you evaluate that integral using your substitution or whatever weird tricks you guys have nowadays, it becomes, I always forget, it's like y over x squared, y over x initial squared times 1 over root x initial squared plus y squared from a to negative a. So that's the solution to the integral. You can watch my video and you can learn where that comes from. So we get b is equal to mu naught I x initial over 4 pi. You're going from, so I guess I'll just write this out. It's going to be, right, you're substituting a in for y. So it's going to be a over x initial squared times 1 over square root x initial squared plus a squared minus negative a. So when you're minusing negative, it just becomes adding. Plus a over x initial squared times 1 over square root x initial squared plus negative a squared, but negative a squared is just a squared, so I'll say plus a squared. So this really just becomes 2a over x initial squared times 1 over x initial squared plus 1. Because we have 2 of these, right? So it just becomes 2 times this stuff right here. So I would say, let's just move this over here. This would become b is equal to mu naught I x initial times 2a. Alright, I guess we can do it like this, 4 pi times 2a over x initial squared times 1 over square root x initial squared plus a squared. Okay, oh my god. X initial on top, x initial squared on bottom. I can get rid of one of those. And then this 2 on top goes away because we have a 4 here. So that becomes a 2. Just simplifying there. What I get now is, and then I can, move this over here. You're going to see we get b is equal to mu naught I over 2 pi x initial times a over square root x initial squared plus a squared. Whew! Oh my god. This is crazy. We're almost there really. So you have the mu naught I over 2 pi x initial. That's just that formula, right? That we're trying to prove. But then we have this nasty stuff. One thing you probably noticed in physics 2 is that when you're doing these kind of problems, when you're dealing with current carrying wires and the magnetic fields they produce, you never have to worry about their length. And this formula is saying, well, hey, you gotta know their length, right? Like you gotta know A, right? How long it is, or half its length, whatever. You gotta know what that is. But what gives, right? Like you never need no length in those problems. Well, it's because we assume that the length is actually really, really, really long compared to the distance you are from there. So you could treat it like A is infinity, right? Like it's this infinitely long wire, but and when you're really, really, really close to it, it actually, that's actually very accurate to the actual magnetic field. Like when you take that limit as A approaches infinity, the top approaches infinity, square root a squared, if you've taken pre-calc honors or AP Calc, you'll know this limit. It's like a infinity here, infinity squared, take square root of that. This, when you take the limit as a approaches infinity, it really boils down to mu naught I over 2 pi x initial times, and the limit evaluates to 1. So there you go. B is equal to mu naught I over 2 pi x initial. There you go. That's where the equation comes from. Just take an integral, use Biot-Savart law, take a limit. There you go. So yeah, hopefully this video was at least somewhat, helpful is maybe a stretch because you really don't need to know this. But if it was interesting, my job here is done.